Hello, this video is my verbal explanation for my solutions to the sample problems for exam 1. So let's kind of go through here problem by problem. Let's kind of walk through it and maybe you use the arrow here to point my way along. Number 1 is very simple, finding the vector between 2 points. And if it's specifically labeled as from R to S, in this case, it would be the second point S minus the first point R. So vector RS would just be 4 minus 2 is 2, and then 1 minus 5 is negative 4. That means vector SR would be just the opposite of that. It would be negative 2 and positive 4. So that's really easy. All right, distance between 2 points. This one's not too difficult. Just use the distance formula. It's basically the same distance formula from algebra, except we're adding a third component there, the z. So real straightforward. Now this one, because of the squaring, it won't matter what order you take the points in, like the vector did. So, but anyway, I did it from P1 to P2. I did the second point as P2, X2. So negative 3 minus negative 7 will be 4. And then negative 4 minus negative 1 is negative 3. You square that. So, and then you have 2 minus 7 is negative 5. So 4 squared is 16. 3 squared is 9 is 25. 5 squared is 25. 25 plus 25 is 50. Square root of 50, which is correct. But if the answer choices were to be reduced, it would reduce to 5 square root of 2. Okay. Let's jump down here. This is pretty easy using just basic vector algebra rules. Because remember, you can multiply a scalar. A scalar in vector world just means a number. So you can always multiply a scalar times a vector. It just means you multiply every number in the vector by that scalar. So 4 times u here would be 4 times vector u, which will be, I didn't write it out, but it would be 440. And then minus 3 times v. 3 times v will be 903, but the negative will affect all of those. And it just specified in the question that it wanted it in standard unit vector form. That's the only reason I wrote it this way instead of just regular component form, because it specifically requested that. So that's the same things that have been negative 5, 4, negative 3 with the angled brackets for component form. Yeah, be careful you never confuse component form of a vector with parentheses, which always means a point. So that's not too bad. Magnitude, that's pretty easy. Whether it's plane or space, I just, my formulas always write the formulas out in terms of space, and you can always drop off what you don't need there. So that's easy. Negative 5 squared is 25, 2 squared is 4. Add them together, you got the square root of 29. We basically want to find a unit vector in the same direction as the given vector, and the unit vector in the direction opposite of that. All right, so any vector, of course, to be a unit vector means it has to be magnitude 1, and then to take any vector and make it a unit vector, you just divide it by its magnitude. So the magnitude here would be negative 5. Oh, there should be a 2 there for a square. Okay, sorry about that. But I'm sure you would have figured that out. So 25 plus 144, square root of 169, happens to be 13. So the same direction would be, to be a unit vector, would be just both those numbers divided by 13. And then the opposite direction, all you have to do is just take the opposite signs, because multiplying a vector by negative 1 essentially just turns it the other direction. So all I did was take the answer and multiply it by negative 1. All right. So let's see what we have here. And vector to be 4 times its length. All you have to do is just multiply the vector by 4. And then 1/3 of its length, you just multiply the vector by 1/3. So that's pretty straightforward. So I think that's easy enough. All right. Center and radius of a sphere. Okay, this is just like back in algebra, if you would have done this with a circle. Once again, it just has an extra component z. We need to do completing the square for each to get it into this form right here. So there wasn't a number term here. If there had been a number term, I would have moved it over. Let's say on the left side there would have been a 10. I would have moved it over and we'd have been starting out with negative 10 on the right side. I want everything else on the left and then whatever number there on the right, but there was not one in this case. All right, so I grouped the x's and the y's and the z's together. And I didn't write it here, but I'll say it verbally now. Completing the square, you take 1/2, what I call the middle term. If you're thinking of like ax squared plus bx plus c, the quadratic equation, the b. You take the b over 2. So half of 2 squared is 1, but 1 squared happens to be 1. Now the next one, half of negative 6 is negative 3. Negative 3 squared is 9. And then half of negative 18, is negative 9. Squared is 81. So we added 3 numbers there in the light blue. You can see 1, 9, and 81. And of course, to keep any equation balanced, whatever you add to one side, you have to add to the other. So the idea is if you're, even if you are starting with a negative number on the right side, of course, the radius can't be negative, but you will add enough numbers to it to make it positive. And then you factor them into squares. That's the whole idea of completing the square. You're guaranteed they'll factor into squares like this. And of course, be careful that of the format these are written in. So if this is x plus 1, that means your x0 value, your first number here of the center, is negative 1. It's always the opposite sign because the equation is written in minus. So that's y minus 3, which makes the y component positive 3. And then z minus 9 makes it positive 9. And then, of course, the radius r will be the square root of whatever number that is. And square root of 91, we don't need a decimal answer to that. That's perfectly fine. Of course, if it was a reducible square root, then we would do that. And that's essentially it for how to find the center and radius of a sphere. Now, you can get more creative with this. I generally don't, so on my exam, you wouldn't have to worry about it. But they see problems in books where sometimes they'll give, okay, you've got 2 endpoints of a sphere across from each other. Okay, you can do that too. That's where you would just take the midpoint between the two, and then that would be your center, and then you'd find the distance from the center to either point. But I'm not going to get too creative on this for testing purposes. If you understand this, that's good enough. Let's see, what do we got here? Parallel, perpendicular, or neither. Now, neither would just be by default. If it doesn't make the first two, it just falls into neither automatically. It doesn't matter whether you check parallel or perpendicular first. I just checked parallel here first, and I was just kind of looking to see if they are a common multiple of each other. That's all we're looking for. Well, pretty easy. In other words, I just use a C here as that common multiple. Well, you see 4 over 4 over 4. Well, okay. Obviously, you see the next. Well, if the first two are 4, that would have meant the next two coordinates would have been exactly the same number. Since it's 5 here, the next one would have been 5. But either way, they have to be a common multiple. So if the first component of A was 4, and the first component of B was 8, and the second component of A was still 5, that means the second one for B would have to be 10. So they would have to double in that case. All right. So it's not parallel. Dot product's real straightforward. Dot product, checking for perpendicular is using the dot product. If the dot product equals 0, you have perpendicular, or also known as orthogonal. And this one turns out, you do a dot product, you get 4 times 4 is 16. 5 and negative 2 is negative 10. Negative 3 and 2 is negative 6. So 16 minus 10 minus 6 equals exactly 0. So those are orthogonal vectors. Perpendicular vectors. Same term, essentially. So that was number 8, I believe that was, yes. Now the vector projection. So you see, use the projection formulas here. You can project a vector along the same path as whatever you're projecting it onto, and then you automatically have a orthogonal vector, which will be this case, the W1 is the projection vector. So you're basically taking a vector and you're breaking it down into two vectors. One of them's along the same path that you're going on to, and then the other one's perpendicular to it, where together they add up together to be your vector. So we're projecting U onto V, and you see W1 is the projection, which is going along the same route as U, and then W2 is just U minus W1, because W1 plus W2 equals U. That's all in my notes, and I'm sure you can see, I have a visual explanation of that too, so I just didn't bother to put it here in the review. So always go back to the notes if you're not sure about something. I didn't show as much detail here as I would have in the notes. So there's the formula. It's pretty easy to use, just following a dot product of the two over the magnitude of V. And so all that's going to be a scalar in the parentheses. Dot product's a scalar, magnitude's a scalar. So you're coming up with some multiple right here, and then you're multiplying the vector by a scalar multiple, which then, of course, yields a vector. All right, so U dot V, I won't worry about going through the dot product. I'm sure you've got that mastered. I know sometimes in face-to-face classes, I can tell students are getting tired of me showing the dot product because it's easy. But anyway, all right, so you see here it is. Here's each of the numbers, and I get 61. I didn't actually write out the magnitude of V. Sorry about that. Well, I'll go ahead and I'll just kind of explain it real quick. I'll just go through it verbally, but that's also easy, but I don't know why I didn't write that down there. So it would just be 3 squared, 1 squared, 3 squared. So it's 9 plus 1 plus 18, all under a radical. So it would be the square root of 19. The actual magnitude is the square root of 19, but this formula shows that you're squaring that magnitude. So basically you're getting rid of the square root. So the fraction here ends up being 61 over 19. So then it's just taking vector V here and we're multiplying each term by 61 over 19. So 3 times 61 over 19 would be 183 over 19, which is the same component for the K. And the middle one is just negative 1 times 61 over 19. So there's your projection vector of U onto V. Find the angle between two vectors. So we can most likely assume they're not going to be orthogonal or perpendicular or parallel. Parallel would make no sense. There'd be no angle between them. Perpendicular, they'd be 90. That's another problem too, where it could ask you, are the vectors parallel? I know that's in the notes somewhere when we're finding vectors. Parallel, perpendicular, or neither, then if neither, find the angle. So the question we did a couple of questions back did not ask for the angle. But we could have found the angle using what we're about to do right here. But that one actually, though, that answer was perpendicular, so it would have been pointless to find the angle. It's automatically 90 degrees. So yeah, a lot of times with neither, you have to find the angle. But no problem, let's follow this. So the formula is cosine of U dot V over the magnitude of U times the magnitude of V. So that means the angle theta, I didn't actually write that out here, but I'll just say it right now. Theta will be the inverse cosine then of that result, all on the right side. Okay. So U dot V, okay, dot product, simple. 2 times 3 is 6, negative 12, and 50. So negative 6 plus 50 is 44. Magnitude of U, and I'll just kind of square these, so it'll be 4, 9, and 100. Add those together is 113, square root of that. 9 plus 16 plus 25, that adds up to 50. So it's the square root of 50. And I put it so you see I have theta equals cosine inverse, all that. Now notice in the calculator, very important that I kept these two, everything on the bottom especially. So the whole thing's in parentheses, but the denominator needs to also stay in parentheses by itself. So you see I have that extra radical in there. But anyway, extra radical, extra parentheses, or at least I think I do. Still might be missing one, but it worked out right. Or you can just multiply those two numbers together under the same radical if you want to. But be careful how you nest, the order of operations, so those two stay on the bottom together. And I get 54.17 degrees. Of course, most likely the question would be in degrees, but just check your calculator mode to make sure you're either in, whatever the appropriate If it wants degrees, make sure it's degrees. That's most common. But, asking it in radians is not unheard of. So we would just check your calculator mode and you're covered either way. So it takes care of that one. Number 11. All right, cross product formula. So obviously you should have that one, in front of you, so you certainly don't need to memorize it. Some of you, the book talks about, many books show how to do it using determinants, what's called determinants in matrix algebra. And that's fine. If you do it that way, that's fine too. I'm not going to really go over that or worry about that, because it's just can be done with this formula right here. You don't have to even worry about. So if you've had any kind of linear algebra background or whatever, it's okay if you don't know what a determinant is. That's fine. Just follow that formula. So it's the U2 V3, so the second component of U and times the third component of V minus U3 V2, so forth, so on. Now I'll walk through this one carefully, and then when we come to cross products, later on down in other examples, I think I'll just skip those steps. And you can always, drop me an email or something if you think something's wrong, but if you're not sure what I did. But this is another one. Well, it's a little more challenging than dot product, but this is another one that, as long as the students have the formula, they don't usually need me to walk through it too many times. Okay, we can do it, we got it. But let me just do it once for you here. So, all right. So okay, U and V, we have A and B. So I'll treat A as U and B as V. So the second U2 would be -1, and then V3 would be 2. So it's -1 times 2. Minus U3, which will be the third, U3 V2. Oh, I wrote them in the wrong order. I'm sorry, but mathematically that makes no difference. I should have put the 1 first and the 3 second. Okay, sorry about the order there, but it's correct. It's the right two numbers. Let's move over to the middle. U3 V1, so it's 1 times the 1 for the I, 1, 1. And then minus U1 V3, which is 2, and V3 is 2, 2 and 2. The last one is U1 V2, it's 2, and then V2 is 3, so it's 2 times 3, minus U2, which is -1, and V1, which is 1. So once again, these are in the wrong two order again, -1 and 1, but that's okay. They're the right two numbers, and of course they'll multiply to be the same. So I guess I just sort of I knew what two numbers they were. I just didn't bother worrying about writing what order they were in. Sorry for any confusion. And just perform each of these simple little arithmetic steps here. And I got -5, -3, and 7. Of course, one of the geometric properties of any cross product is a cross product has to be orthogonal to both vectors you crossed it with. That's one of the important geometric features, especially, equations of planes, is that, you cross two vectors, you guarantee you get a vector that's orthogonal to both of the other two original vectors. And then what that means is this answer of course, it could still be wrong, because you actually cross in the wrong order, you could get the negative of this, and it would still be true for what I'm about to say. But if you dot product this answer with both those original vectors, it should yield 0 to make sure it's orthogonal to both of those. Because what I was saying here is if you cross them, forgot the little arrow here. If you cross them in the wrong order, they would still be orthogonal, but it really wouldn't be specifically A cross B. It would be B cross A, reverse it. That would still be orthogonal, but it wouldn't specifically be the one they're asking for, A cross B. That's what I meant. So in other words, if you did B cross A and just did the dot product check, yeah, they would yield 0, but it still wouldn't have been the right answer. But obviously, if at least one of the dot products does not yield 0, then you know it's wrong. Let's take a look at number 12 here. We've got a rectangular vertices, and we're finding the area of a triangle. All right, so and there is a fourth point here, but it's just 0, 0, 0. But for the triangle, it doesn't really matter. All you have to do is, for those 3 points, is create any two vectors out of those three and do a cross product, take the magnitude of it, and then take half of it. If we brought 0, 0, 0 in there as a point, and that's in my notes too. You can go back and look at that, and I explain that. You could get two vectors again, cross product, take the magnitude, and then that would be the area of a parallelogram. But the triangle is just half of that. So we have to remember, I misspelled triangle there. Not triangle. All right, all kinds of little mistakes here, but no major math mistakes. That's the good point. That's the good part. Let's see. So I just chose PQ and PR. I could have done QR, but I just didn't. I just picked any two vectors to cross together. So obviously PQ, then you take 3 minus 1 will be 2, 4 minus 2 will be 2, 5 minus 3 will be 2. It'll be the vector 2, 2, 2. And then PR will be 0 minus 1 is negative 1, 1 minus 2 is negative 1, 0 minus 3 is negative 3. There's your two vectors, and it's going to be half. Here I wrote the numbers for the cross product, so I promised that I wouldn't go through all the cross product steps again. Now, this would actually not matter which order you cross them in. In other words, you could have put PR first and PQ second, because we're just going to find the length of it, the magnitude, so it doesn't matter. But anyway, when I crossed them in that specific order, PQ, PR, I got negative 4, 4, 0. The magnitude of that would be the square root of 16 plus 0, which is the square root of 32. And the area will be half of that. The square root of 32 reduces down to 4 square root of 2, and half of that will be 2 square root of 2. All right. The volume of that, you can look in the notes and see a picture of it. It's basically like a parallel three-dimensional solid thing. It's not a rectangular solid. It angles like a parallelogram. It's the volume of I can't ever pronounce that word, parallelopiped or peeped or something, whatever. But it's a three-dimensional parallelogram. You can use any combination of the vectors. Now, if you look at these vectors I came up with, I'm calling them U, V, and W. I'm doing OP, OQ, and OR. It looks like I just magically took those points right there, P, Q, and R, and just automatically named them made them into vectors. No, I didn't do that. That would not be correct, but it's just coincidentally working out that way because I'm using O as my starting point, 0, 0, 0. So obviously when you take all three of those points and you're creating a vector from the origin, the vector will be the same thing, numbers as the point, because you're subtracting 0 from all of them. So that's what's happening is because, using 0, 0, 0. So there's U, V, W by creating those three vectors. And I think I showed this in the notes with a couple examples there with doing it in different orders. Even though it says U dot V cross W, you can cross any two of the vectors and dot it with the other and take the absolute value of it. Sometimes it'll come out negative. What order you choose, but the absolute value, so it works no matter what. This one happened to work out where it was already positive on the inside, but the absolute value is what protects. It's obviously got to be positive. Dot products are allowed to be negative. That's fine, but this has to be a positive result because it's measuring volume. So but any order. But I went ahead and followed the formula as it was based on how I named it here. So I did a V cross W using the cross product formula. I'll spare you the work on that. So it's negative 5, 0, 3. And then I dotted that with the vector. 1, 2, 3. And it ends up being positive 4 on the inside. Then the absolute value of it makes it 4. But my point is you could have done U cross V, got that cross product, and then dotted it with W if you wanted to. And you still would have gotten 4. You might, with the absolute value, you would have gotten 4. So that's not a bad plug and chug formula there. It's not too bad. Let's come down here. We have two vectors, 1, 2, 3, and 4, 5, 6. We're going to find two unit vectors, different unit vectors, U and V, which are perpendicular to both A and B. So that, once again, I was saying earlier, that's what a cross product is. That's what it's giving you. It's giving you the vector. That's taking care of the perpendicular part. So doing the cross product, that gives you the perpendicular vector here. -3, 6, -3. But then now it's saying it's asking for unit vectors. So that means to make it a unit vector, we have to find the magnitude of that cross product. So we have to divide by that magnitude. Now, I used a property that you can use when you're finding magnitude, is if you want to pull out a common factor, you can. You don't have to, but I always like to. I pull it out, and you take the absolute value of it. So this always, magnitude is always length. It's always positive. So it's the absolute. You could have pulled out a 3 if you wanted to, but I went ahead and pulled out a -3. So it left me, but the absolute value is still going to make it 3. So I have 1, -2, 1 on the inside, which will give me the square root of 6 when I do that magnitude. So basically, the unit vector 1 over 3 square root of 6 times -3, 6, -3. And the 3 divides evenly into all three of those. So you have, U and V, two different vectors. It didn't say opposite direction, but I guess that's what it implies here. I just made it the opposite direction. Should have said opposite direction in there. But anyway, so it's -1 over root 6, 2 over root 6, -1 over root 6. And then I just took the negative of it, so it would just be going the opposite direction, which is fine. That's fine. Now, when I have handwritten tests and things, I'm a kind of person, I don't care about radicals in the denominator, but, in your exams, they might be rationalized. But you could always check them, via decimal equivalent if you wanted to. If you think you're not sure about, you can check 1 divided by square root of 6. But it's not. This is an easy one to rationalize, for sure. Just multiply top and bottom by square root of 6 over square root of 6. Yeah, square root of 6 over square root of 6. So there they are, rationalized. And there we go. All right. Okay, parametrics of a straight line that passed from P1, point P1 to P2. All right. We're going to need a direction vector between those 2 points. So, to do these kind of problems for parametric equations, you either have to have a point and a given direction vector, or if you have 2 points, you can then calculate the direction vector. So either way, so this one has 2 points, no problem, easy vector calculation. So 8 minus 2 is 6. 1 minus 4 is -3. 3 minus 6 is -3. So that's your direction vector ABC in this formula right here. X0, Y0, Z0. Could actually be either point, but I'm going to go ahead and use the starting point for simplicity. But actually, either point is acceptable because both those points, have to be on the line anyway. So there you go. So I'm using 2, 4, 6 as my starting point. So there's 2, 4, 6 right there for X0, Y0, Z0. And then the coefficients are 6, -3, -3. So it'd be 2 plus 6t for X. Y is 4 minus 3t. And Z would be 6 minus 3t. All right, so let's look at number 15. Line passing through a point that's perpendicular to a plane. That was covered in 11.5, I believe. But anyway, well, the direction, if it's perpendicular to the plane, that means the line direction is going to be going the same direction as the normal vector to the plane. Because, the plane is going to have a normal vector sticking out of it. That means they're going to be parallel. So the normal vector to the plane, which is always given by the coefficients of x, y, and z, that's your normal vector. That's going to be the direction vector for the line. So once you realize that, it's real straightforward. So 4, 6, 4, that normal vector is also, or any multiple of this would actually be acceptable because it just has to be going the same direction. You don't need to. I'm just mentioning that because it's true. Like technically 2, 3, 2 would have been correct. because all we need is a direction vector. We don't care about its length. Yeah, so there you go. So your point's negative 1, 2, 0. So we have negative 1, 2, and then of course 0 doesn't need to be shown. And then your coefficients of t will be this normal vector here. Will be 4t, 6t, 4t. And there we go. And let's see, number 16. Find an equation of the plane with normal vector passes through a point. All right, that's pretty easy, because it's giving you the normal vector and it's giving you the point. If you have the normal vector and a point, you're good to go. And there's the equation of the plane. There's the standard equation in standard form, general form, and I'll explain that here in a minute. Because obviously, being multiple choice, you're going to be looking at the answers, so you'll know what it wants. So here's how you get it started, though. So you start with standard equation, no matter what, and then if you have to convert it, then you convert it. So it would be, the normal vector would be 3, negative 2, 1. So it's 3 times x minus 6, and then minus 2 times y minus 2, plus 1, z minus a minus 5, so it'd be z plus 5, that equals 0. So then you got to look at your answers. We'll assume it looks like this. Sometimes I've seen them where the 9, it could be in standard form, but a lot of times they're in general form. Sometimes the 9 might be over here and it might be set equal to 0. So you just look, you're just looking at the answer forms and seeing which one you have to match. So that means you just do a little simple algebra here. You just have to distribute. That's easy enough. So that gives you 3x minus 18. And then negative 2 distributed would give you negative 2y plus 4. And this gives you a z plus 5. So what happens is you add the numbers up, you'll get negative 9, and then move it over, and it makes it positive 9, so in case if it looks like that, that's what you'd be looking for right there. So once you kind of get it started in the standard form, it would not be hard to get it converted over to find the right answer. Very good. Ah, yes, this is a classic one that I use also. This one's weird. I decided for some reason to set this equal to 0. But, once again, I'm jumping ahead. That's okay. It could have been moved over and been negative 8 on the other side. But once again, that shouldn't be hard for you to figure out. So the last problem gave us a point and the normal vector. That's good enough to get an equation. Now, we saw a few problems back for a line. If you have a line and the direction vector, you're good. Or if you have 2 points on the line, you're good. But 2 points is not good enough for a plane. You have to have 3 points. So that's why it's important we have all 3 of those points. So all you have to do is come up with any 2 of the 3 possible vectors between those points. There's a PQ, a PR, and a QR. Any 2 of those. I just did PQ and PR. And then to get our normal vector comes from the cross product. Because remember, the terms normal, orthogonal, and perpendicular are all kind of basically the same thing. They mean, but just it's used. Normal is used with a lot of times with orthogonal is used with vectors, and so it's just kind of used at different times. But any of those mean the same thing, 90 degrees. So I have to get the normal vector, which was given in the last problem, I have to do a cross product of these 2 vectors right here. So negative 3, 2, and 1. Now, because all 3 of those points have to be on the plane, I can use any of those 3 points as the x1, y1, z1, any of them. I just said I chose P, but any one of them is fine. So here's your negative 3, here's your 2, here's your 1. And then I have x minus 1, y minus 3, and z minus 5, because I'm using the point 1, 3, 5. I distribute it out like so, easy enough. And then I have negative 8 here, so this time I left it, but I could have moved it over. Now here's where we're going to be careful. Let's say you look at this answer, and you're looking at your answer choices, and you don't see you don't see that answer. But you see what's over here to the right. Well, actually, those are equivalent, because if you see this answer on the left, if you multiply both sides by -1, it's going to yield that answer on the right, which means they're equivalent. So essentially, these kind of problems with x's, y's, and z's or whatever, and if all the signs are the opposite, in other words, every sign is the opposite of what your answer is, that is the correct answer. They have to all be the opposite. That's a key. Because remember, with equations, whatever you can multiply the same number to both sides, and it's still the same equation. So this one, that's what happens. So I just multiply both sides by -1, and then there we go. So that way, don't let that confuse you. That's easy enough. So if your answer doesn't match, look for the answer that has all the signs opposite of yours. And if you did it right, that will be the correct answer. All right. Now, got a plane that contains a point, and then we have an equation for the line. The plane, in other words, that line is on the plane, and then that point is on the plane. Now, it doesn't mean that point's on that line. Now, you might ask, how could you tell if it was or it wasn't? That's a good question. Is because if this point, 135, is on that line L, that means there can be a value for t that would produce that point. Well, let's check this. So let's look at the first one. So if it's 4t, t would have to be 1/4 to give us 1. So if I put in 1/4 for t and the other two components, they're not going to yield 3 and 5. So that's how I know it's not on the line. Hey, notice my answer here, or any multiple of this equation. That also includes, the last one I didn't mention, that also includes not only signs, but let's say if your answers could have been reduced, in other words. Let's say, like going back to this last one, what if by somehow you had 6x minus 4y minus 2z plus 16 equals 0? That's also the same thing as the negative issue I talked about, because you can divide everything by 2. So that's what I'm saying. When you're looking for matching answers like that, just a lot of times they may be in the most reduced form. All right. So what I need here is a point on the line L. I need a point on the line. And let's see what we have here. So I'll just pick any value for t. Anytime you need a point on a line that has a parametric form, just pick a number for t. I'll pick 0. So that would give me, put in 0 for t here, I would get 0, 6, and 3. So I got this point P, Q now, I have point P. Now I already have that line has a direction vector. So technically the direction vector of that line would be the coefficients of the t's, would be 4, 5, and -2. So I have one vector. Now I need a second vector to be able to do my cross product. So to get a second vector, all I have to do is create a vector between the point P and the point Q. Let's create that vector. So we have one vector, we'll have another vector, then we can cross them, and we've got it. So I just called V your direction vector. Here's my PQ. Okay, that's easy enough. Take point Q minus P. We already know how to do that. So I got -1, 3, -2 for that vector. So I didn't show the work for the cross product, but you can obviously double check that yourself for practice, which is a good idea. I have the cross product formula, several problems earlier. After I copied it once, I didn't bother pasting it with every problem. I knew you could find it. So I got 4, -10, and -17. So those are here's my A, B, C right here, 4, -10, -17. I just chose point P to put in here, which will be x minus 1, y minus 3, z minus 5, like so. And then distribute all that out. So you got 4x. Looks like I kind of skipped a couple steps there. Not all I skipped was the arithmetic. You see the 4x, the minus 10y, and the minus 17z. But I should have had a -4. -10 times 3 is 30. And then -17 times -5 is 85. So 85 plus 30 is 115, minus 4 is the 111 right there. So once again, the 111 could be on the other side. So they could have said equal to negative 111. That would have been fine. And then there we go. So once again, look for the opposite signs or anything, when you're matching answer choices. Just in case. Very good. Let's come down here to number 19. Determine whether the line and the plane intersect or parallel. If they intersect, find the point of intersection. All right, so let's see what's going on here. The direction vector for the line will be negative 4, 6, and 5. The normal vector for the plane will be 4, 1, and 2. Now, to determine what I'm going to do here is the dot product. Because the dot product is 0, that means the direction vector for the line and the normal vector to the plane are perpendicular to each other. Therefore, because the normal vector of the plane is already perpendicular to the vector, and if the line's perpendicular to that, so it's kind of like perpendicular to perpendicular creates parallel. Of course, I'm sitting here demonstrating this with my hands, and no one can see it. But anyway, yeah, so like perpendicular to perpendicular is parallel. So that means that line is going to be parallel to that plane. They're never going to intersect. All right. Now this one is not, I could have done the same thing for the next one, but it's pretty much telling us that it's not going to be parallel. In other words, we'll have to even check that if we don't want to. But I did. The dot product of the two vectors, like I did, is not 0, so we're going to have a point of intersection. Now it is possible that the line, if the line is on the plane, you don't really have a specific intersecting point because it would theoretically be infinite points. So that's always a possible answer too. And that's going to happen. What would happen in that? Well, let me start the solution process of this, and I'll tell you what you would have been looking for there for that to happen. So we either have, now at this point, they're not going to be parallel, so they're either going to have, either the line's going to kind of angle through and only hit the plane once, or the line's going to be on the plane and it's just infinite points. That would make it true. Doesn't mean all real numbers. It means just whatever point that's on the plane would also be on the line. On the line would be on the plane. Yeah. Said that in the wrong order. So let's see. We're going to take to solve, because we want to find the value t where the line hits the plane. So I'm going to take the values for x, y, and z in terms of t and substitute them into the equation for the plane. So the 3t is going to go in for x down here. 7 minus t goes in for y. And then 4 goes in for z. And let's see. So you kind of work this out pretty easy. 6t, so be careful with the negative. Negative 7 plus t plus 8 equals 10. And then solving for t, you get 7t equals 9. T equals 9 over 7. Now what I was talking about here is if you would have had the line on the plane, the t's, you would have had a equality. So you would have got like 10 equals 10. You would have got, in other words, true for the t's would have gone away, and you would have got 10 equals 10. Now, ironically, if you would have got something that was like 6 equals 10, a contradiction, that would have meant the line was parallel to the plane. So we know we're not going to get that because we've already eliminated that, meaning they would never hit each other at all. That's the only way a line and a plane would never hit each other is the parallel. Same idea as if it was two lines, like back in algebra. But here, let's say if I would have got like 10 equals 10, that means it would have been on the line, would have been on the plane. But anyway, it's not. So only when t equals 9 over 7 will that point line hit that plane. And then to find what point that will be, that's not too difficult. You just plug the 9 over 7 into the values in the parametric equation for the line. So you get 3 times 9 over 7, which is 27 over 7. 7 minus 9 over 7, common denominator, 40 over 7. And z is just fixed at 4. So there's going to be your point. And then if you wanted to double check that, since the line's hitting the plane, and I've checked this before, I've not worked it out, but you might want to try it. It won't be that bad. Is take that answer and make sure it's true in the equation of the plane. Because obviously if it's true for the line, it's got to be true for the plane, because that's the one point where they're hitting each other. So if you want to plug that in there, I guess I'll do it real quick verbally. It wouldn't be that hard. 2 times 27 over 7 is 54 over 7, minus 40 over 7. So it'd be 54 over 7 minus 40 over 7 is 14 over 7, which happens to be 2. And then 4z, so 2 plus 2 times 4, 2 plus 8 is 10.